everybody, this is Elisa. Welcome back. We're doing the respiratory system. So now we're going to get into a multi-part of gas exchanges. Things to know, you don't breathe in pure oxygen. It's really only about 21% of the air we breathe. Like, it's mainly nitrogen, but it's not like super reactive like oxygen is. There's a small amount of carbon dioxide. And then depending on like where you live, the temperature, the pressure, there can also be humidity of up to 4%-ish. There's also some other stuff like helium and methane and ozone and all this other stuff. But really, like the take-home message is there's not a lot of carbon dioxide and there is 21% oxygen. And so that's whenever you'd never give a patient like, 100% oxygen unless the flow rate was titrated down to about 21%. Okay, just things to marinate on in case you're going into this stuff. Okay, so let's talk about the site of gas exchange versus the alveoli in the lungs, right? Remember, they have the capillaries on the surface of them, and they're swapping, right? There's surfactant, a basement membrane, and so we're swapping gases like in and out, right, to get pulled out by the bronchioles. So there is that, or put in. So we swap actually. We actually swap oxygen. So red blood cells have like a higher affinity for oxygen and a lower affinity for carbon dioxide. But like if oxygen isn't around, it'll definitely grab that carbon dioxide. And it's also carbon dioxide is dissolved in the blood plasma as well. So there's that. So that's the point. So we're going to exchange some gases. We're going to get rid of carbon dioxide, which we used up during cellular respiration, which is different. And we're going to bring in some fresh reactive oxygen, right, to fuel some more, electron transport chain goodness. Anyway, so the air in the alveoli is in contact with like this film of water, surfactant actually, that covers the alveoli, right? And so for oxygen to get into the blood, it has to like kind of go through this layer, right? It has to travel like through this layer, which is helpful. It's called it dissolves through this membrane, and then that's how it moves into the bloodstream, into the capillaries itself. But for carbon dioxide to leave the blood and to go into the alveolar space, it has to pass the other way. So it diffuses out of the water and it floats up little bubbles into the alveolar space, right? So the gases are going to be diffusing through their gradients. So it means this. So like here's like the deal. So let's say here's oxygen and here's carbon dioxide. And like the red stuff is, guess what? It's your blood. And so there's, in this case, like not a lot of oxygen in the blood, right? And so what ends up happening is the oxygen that's in the air starts wanting to diffuse down the concentration gradient, right? Until we reach like equilibrium. Do you remember diffusion? Right? That's what it always wants to do. Until we have like equal parts here to here, right? And so it spreads out. It wants space. It wants its own space until like, everybody's got equal space, equal distance, equidistance, right? And so carbon dioxide is actually initially the reverse. So in the bloodstream, there's usually like a decently high concentration of carbon dioxide. So by the time it reaches like the alveoli and the surfactant on the alveoli, it's like ready to like bubble up and diffuse back into the air where like there's not a lot of carbon dioxide, right? So, oh gosh, here, come on, let's go back. Let me see. Where is it? There it is, right? So remember, there's like not a lot of carbon dioxide in the air, and there's like a decent amount of oxygen. So like oxygen wants to move into the lungs, and carbon dioxide wants out, right? Where there's like low amounts of carbon dioxide for really high amounts, right? And like vice versa. So diffusion, that's the jam. And so it has to do with like how much air, is actually naturally in the air. Okay, right, we talked about that. Yeah, okay. Okay, next. So anyway, so gases are going to be diffusing down their own gradients, so we looked at that until the partial pressure of each gas is equal to the partial pressure in water. So equilibrium is what we're looking for. But there's like this thing about water and air, and we call it Henry's law. So like right where air and like water interface, there's stable temperature, like temperature, remember always, if there is higher temperature, it adds energy into the system and it changes how much the molecules will want to move. So remember that. Um, the amount of gas that's going to dissolve into the water is determined by its solubility in water, just like in general, and how much of it is in the air, like pressurizing is the air. This is like, how we get carbonation into fizzy drinks, right? This is like in that ballpark, right? We can actually force um, gases through into to liquids where they can like literally dissolve, right? And then when there's too much of them, they bubble up and become little bubbles, right? So the greater the pressure of oxygen is in the alveolar air, the more oxygen the blood is actually going to want to grab onto because it's like, like lower pressure into the blood. So of course it's going down that concentration gradient. And then the blood that's arriving at the alveoli usually has like a ton of carbon dioxide. So it wants to go out into the air where there's like not that much, as we saw, like 0.04% carbon dioxide. So that's where it bubbles up and releases out into the air. At the alveoli, the blood is, generally you're saying we're unloading, we're expiring carbon dioxide, and we're loading oxygen, right, into the bloodstream. So we're unloading carbon dioxide, breathing it out. We're loading oxygen, that's why we're breathing it in. And so now we're involving the erythrocytes. Erythra meaning red, and the cytes meaning cells. So these are the red blood cells, the RBCs, right? So generally, it's kind of quick. This is pretty fast, and it also depends on how fast the blood is moving. So it only takes about like a quarter of a second. Oh, there it is. I mean a two, but it was supposed to be a four. A quarter of a second to reach equilibrium, right? So this is like a fast process, like relatively fast. And so if the red blood cell is like just sitting there like kind of not going super fast, it'll actually spend like quite a bit of time in the alveolar capillary, so it definitely picks up the oxygen it needs to pick up, right? However, when you're like running, oh my gosh, your heart rate's like for me, like my high heart rate is like 155. I hit that, I'm like, whoa, I'm sweating. um, then it means that your blood is like physically moving faster. That means it's only going to be sitting in that alveolar capillary for like 0.3 seconds, like a third of a second, right? But that's still enough, boop, 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 to get the oxygen you need, right? Because remember, you just have to have it there for like a quarter of a second. So each gas in a mixture behaves independently. It's just like the oxygen only cares what the oxygen around it is doing, and the carbon dioxide only cares what the carbon dioxide is doing. Okay, so they don't care what each other is doing. They just care what, they are doing. Okay. Oh, yeah, we looked at that. There you go. Okay, so the pressure gradient of gases. So normally the pressure of oxygen is 104 millimeters per mercury in alveolar air versus like 40 millimeters per mercury in the blood. So like it's higher pressure in the alveoli and it wants to get into the blood because it's lower pressure, right? And then the pressure of carbon dioxide is like 46 millimeters per mercury in the blood versus like 40 millimeters per mercury in the alveolar. And even though it's like only a slight difference, it's enough for the carbon dioxide to want to go to the air because it's going to be like, it's just lower pressure and that's all it takes. There's a concept of hyperbaric oxygen therapy. So what that means is we have like treatment with oxygen at greater than 1 atm of pressure. And the idea is you're driving oxygen faster into the blood. Maybe you're like, have some kind of resistance for whatever reason. And so that like would theoretically help by just really forcing the pressure higher. So it forces the oxygen into the blood more efficiently, hopefully. So that's what that is. So we'd use that to do things like, various treatments like gangrene actually, because these microbes are like not loving oxygen, and also carbon monoxide poisoning can restabilize the oxygen levels in the blood because of the reactivity. At higher altitudes, the partial pressures of all gases are just lower. And so in some cases, it's interesting how people adapt. Like, so some people at sea level have like, the size heart, but then you'll go and look at people who live at, say, like in the Andes, and they'll actually have like a physically larger heart, right, for pumping more blood. Some people have an increase in RBCs, right? in red blood cell production just like jumps up, right? So if you come from sea level and you come to Albuquerque, where we are, and you have a margarita when you get off the plane, it is going to hit you like a ton of bricks. And if you give it like a while until you're able to kind of deal with the pressure changes, then it's not so dramatic. So yeah, just be careful. Don't have a drink right off the bat. Okay. So we'll talk about the circulatory route in a bit, but I hope that was helpful, getting you started. And I hope you're out there somewhere having a really great day. Okay, bye bye.